Hi, this video is meant to go over a few examples in P7 that we didn't get to. We did talk about complex conjugates, and that's what this kind of follows is starting on page 69 and 70, just dealing with operations with complex numbers. So I'm going to start with the theorem for complex conjugates. And this theorem says if A and B are real numbers, then A plus BI times A minus BI is equal to A squared plus B squared, where A minus BI is the complex conjugate of A plus BI. Basically, you keep the real part and change the sign of the imaginary part. The reason why this works out is because this is the difference of squares. You end up getting A squared minus B squared I squared, but we talked about how I squared is equal to -1. So when you replace I squared with -1, you have a minus B squared times a -1, and so a minus a negative becomes plus. So we see that by multiplying by the complex conjugate, we end up getting a real answer, which is A squared plus B squared. This helps us because if we are trying to divide imaginary numbers, the way we divide imaginary numbers is by multiplying by a factor of 1, where the numerator and denominator are both complex conjugates of the denominator. So the first one in your book is 8 minus I divided by 2 plus I. Sorry, that's a plus sign. What we're going to do is find the complex conjugate of the denominator. So if it's 2 plus I, the conjugate is going to be 2 minus I. And we need to multiply both numerator and denominator by that. When I'm doing this, I'm going to put the numerator and denominator of my original fraction also in parentheses. And now we get to FOIL this out. In the numerator, we get 8 times 2, which is 16. 8 times -I is minus 8I. Negative I times 2 is minus 2I. And -I times -I is plus I squared. And I do like to write that out just to make sure I don't make mistakes. In the denominator, we have a difference of squares going on. And if we follow our theorem here, we're going to get 2 times 2, which is 4. And we're going to get -I times +I, which is minus I squared. But based on this theorem, I'm really getting plus B squared. And if you notice here, the B value is the number in front of the I, which is 1. So we end up getting plus 1 because I squared is really -1. So we're doing minus a -1. Let's simplify this. I'm going to replace this I squared with -1. So in the numerator, what I'm getting is 16. I'm going to ignore the i's. And then -1 is 15. Now I got to look at the I terms. I have minus 8I minus 2I. That's minus 10I. And then in the denominator, I have 4 plus 1, which is, sorry, my pen's not working, 5. Now, if you notice, the numerator has 2 terms in it, and both of them have a factor of 5. So I can actually divide 15 divided by 5 and get 3. And then negative 10i divided by 5 is minus 2i. And so this would be my final answer. Okay, let's do another example. We're going to do 4. Why is my pen not working? Four divided by 1 plus I. So the very first step is to figure out what is your complex conjugate of the denominator. And I would keep the real part, change the sign of the imaginary. And I have to multiply both numerator and denominator by that. The numerator is kind of easy because I'm just doing 4 times 1, 4 times negative I. So this is 4 minus 4i. And then in the denominator, following our theorem, we do the first thing times the first thing. So I get 1 squared, which is 1. And then I have negative I times positive I again. So this is going to be minus I squared. And I could write that out. Or this really becomes plus 1. Because I squared is negative 1. So in the end, we get 4 minus 4i divided by 1 plus 1, which is 2. We can simplify this because both 4 and minus 4i can be divisible by 2. And we get 2 minus 2i. So that's how you divide out by a complex number. Let's look at roots of negative numbers. And we did talk about the definitions. I'm not going to write that down. This is on page 70, the little green box. But I do want to do some examples just so you have them. We did some in class, but it's always helpful to see extra examples. So if I try to do something, I'm just going to go through the first example. Root negative 8 plus root negative 18. I always like to take the negatives out and replace them with I right away. So this is going to be I root 8 plus I root 18. Now, even though there's an I here, you don't want to combine the root 8 and the root 18. You need to figure out, can I simplify this at all? And if you think about 8, you want to look for perfect squares. This is really 4 times 2. And 18 is really 9 times 2. And the reason that helps us is because both 9 and 4 we can take the square root of. And so the square root of that is going to come out of the square root, but the 2 is going to stay behind. So if I think about what the root of 4 is, that's 2. And the other 2 here stays inside the root. And then the root of 9 is 3. And this 2 stays inside. Why does that help us? This helps us because in both of these terms I have a root 2, and really it's I root 2 in common. So now we can actually add this together. If I have 3i root 2 and 2i root 2 added together, my answer, I would just take 2 plus 3 and get 5i root 2. And like I said, the only reason I can do this is because I root 2 is in common. If it was a different root, I can't add them. All right, let's look at example C in your book, which is root negative 27 times root 9 minus root negative 2. Before I do anything else, I like to take out that I, like I said, look for these negatives inside the root. This negative in front of that does not matter, that's a minus, but I'm going to replace this with I root 27, and then root 9 minus I root 2. Now I get to try to simplify roots as much as I can. 27 is really 9 times 3. I can take the square root of 9. I can take the square root of 9 inside of this parentheses, and I can't take the square root of 2. So this is going to become, if I take the square root of 9 and put that square root out here, you have to take the square root. It's not just 9, but that becomes 3i, and notice how there's a 3 left behind, root 3. And then in parentheses, sometimes visually I prefer brackets to parentheses, but it's really whatever you prefer. So this is 3 minus I root 2. And now I get to multiply 3i root 3 times everything inside of that parenthesis or bracket. If I multiply 3i root 3 times 3, that becomes 9i root 3. And if I multiply 3i root 3 times I root 2, this is a little bit messier. I'm going to do this in a different color. I have a minus from here. I have the 3. I end up getting I times I, which is I squared, and I'm going to write that for now. And then I have root 3 times root 2. I can combine those by doing 3 times 2 inside of the root. So that's root 6. But now I need to make sure that I simplify this I squared. Remember, I squared is negative 1. And so the negative and the negative 1 are going to become positive. So I get 9i root 3 plus 3 root 6. That's correct, but typically we write the imaginary number part second. So I would really want to write this as 3 root 6 plus 9i root 3. And that would be my final answer. I'll do one more example, and this is the tried in your book. It tells you to do 2 minus root negative 12 divided by 2 in a plus bi form. My very first thing is to take out this negative and rewrite it as I. So 2 minus I root 12 divided by 2. Notice how I'm not canceling the 2's here like this. I can't do that because there's no 2 in front of the I. So I can't actually do that. I have to simplify this root 12. Well, 12 is really 4 times 3. I can take the root of 4, and that is going to become 2 in front of that I. So this is really 2 minus 2i, the 3 stays behind, divided by 2. And because I have that repeated factor of 2 in every term, now I get to cancel the 2's, and they become 1. So this is 1 minus 1i root 3 divided by 1. This is my final answer. All right, hopefully that helps you with section P7.